Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover variation of parameters, really another way of finding the particular solution to the differential equation, this second order linear differential equation. And I'm going to start out with Cramer's rule, and what I have is I have a system of equations here, and I just solved it using the addition method, getting these things to match so you can cancel the x's, so I can see that y is 10 over 11, and then, plugging that back into, say, the easier equation, I can see that x is going to be equal to 48 over 11. Now, Cramer's rule says that we can use matrices to be able to solve these things, so we'll call this, the determinant of A star. Now, A star would be, if we're looking at this matrix here, we have, this 2, 1, minus 3, 4, and then 6, 8. A star, since I'm trying to solve for x, is I cover up, the x column, and then this 6 and 8 is going to go in that spot, so 6, 8, and then I'm going to use this 3, negative 4. So the determinant of that over the determinant of, our variable part of it, which is going to be the 2, negative 3, 1, 4. And when we do this, we can see that x is going to be equal to 48 over 11, which is what we know. And then for B star, the same thing. What you do is you cover up the B column and you put this in that location, so that you have that 2, 1 vertically, and then 6, 8 vertically, and then against over the determinant of our of really the coefficients of your variables, and you can see that I get 10 over 11. So when we do variation of parameters, it kind of comes down to being able to set up that system of equations and using Cramer's rule to be able to find other solutions. All right, so assumption is that the particular solution is a function u of x times y1 of x, and then a function u2 of x times y2 of x, where your y1 and your y2 come from the complementary solutions, or the homogeneous solution of this differential equation, so when f of x is equal to 0. So we're going to set up the equations that we have this system of equations that y1 u1 prime plus y2 u2 prime would be equal to 0, and the derivative of these y1 prime u1 prime plus y2 prime u2 prime would be equal to, say, f of x. Now, our goal really is to kind of, be able to solve this, and we're going to use, solve for u1 and u2, and what we're going to do is we're going to use Cramer's rule. So, u1 and u2 are going to be in the, x and y positions like we saw with that system of equations. So we can find, u1 prime. Let's do Cramer's rule. Says that u1 prime, which is, kind of in that x location that we had for the systems, is going to be, I'll call this w1 over w, and it's going to be, these would be their determinants. And then very similar, we're going to have u2 prime is going to be, this would be w2 all over the determinant of w. Now, what's going to happen for your w1, since I'm solving for this first column, these are going to be your coefficients, but, these will go in that location, so it's going to be the determinant of 0, y1, and then this is going to be y1 prime, and then f. And then down here is going to be, the coefficient matrix, so y1, y2, y1 prime, y2 prime. And, for u2 prime, this is going to be, well, instead of solving for the first, we're going to solve for the second, and that means these are going to go in the coefficient. So this is going to be y1 and then y2, and this will be y1 prime and then y2 prime. No, that's not right. That would be the denominator. My bad. These are going to go in that second variable location, so this would be 0. This would be equal to f. And do I even have that right? This is not correct. Actually, I almost have that right. So remember that what we're doing is we're taking this coefficient matrix, and instead of having these in the first column, which is where your variable would live, we're actually having these go there, so this would be 0 and f. And then very similar, these are untouched, and these are going to go in the second location. and then, all over the original. So y1, y2, and this will be y1 prime, y2 prime. So the exact same idea that we did with Cramer's rule just a minute ago. So this is kind of our goal, and what I'm now going to do is we're going to have these coefficients, and basically we're going to give us a differential equation so we can actually set up this system of equations, and then I will be able to find these particular solutions, your u1 and u2 primes, and then from there I'm going to have to find u1, and I'm also going to have to find u2. But since I know the derivatives, this is going to be found through the integrals of these pieces. So this is going to be our method. So in order to solve this differential equation using variation of parameters, the first thing you have to do is I'm going to have to find my y1 and y2, and they're going to come from that complementary solution, which really comes from the homogeneous solution. So really we're solving this minus y double prime minus 4y prime plus 4y is equal to 0. So then using our characteristic equation, r squared minus 4r plus 4 is equal to 0. So this thing factors into r minus 2, r minus 2. So we're going to have solutions which are related to the zeros of these things. So my complementary solution is going to be equal to c1 e to the 2t, 2x because our variable is x, and this is going to be plus c2 e to the, well, it would be 2x as well, but that would be linearly dependent. Since it's a repeated root, I'm going to have to put an x in here, so e to the 2x. So this is of that form c1y1 plus c2y2. So this is our y1, and this is our y1, and then this is going to be our y2. So now when I set up this variation of parameters, we know that we have this y1 u1 prime plus y2 u2 prime is going to be equal to 0. And then very similar, we're going to have y1 prime u1 prime plus y2 prime u2 prime is going to be equal to f of x. F of x being this thing. All right, so in order to do these, I'm going to need to know what u1 prime and u2 prime was. So if u1 is equal to e to the 2x, then u1 prime is going to be 2e to the 2x. And if u2 is equal to x e to the 2x, then u2 prime, using the product rule, derivative of the first times the second plus the first times the derivative of the second. So when I do set up this equation, we know that we're going to have y1 u1 prime, which is going to be times 2e to the 2x plus y2 u2 prime, which is going to be this e to the 2x plus 2x e to the 2x, and that'll be equal to 0. And then we have our y1 prime times the exact same, and then this is y2 prime times the exact same u2 prime, but this is equal to f of x, which is x plus 1 e to the 2x. All right, so that means that our w is going to be our coefficient matrix. So this is going to be the y1, y2, y1 prime, y2 prime, which is going to be equal to these coefficients. Make sure that this makes sense. These should have been y's. My bad. I'm gonna have to redo them all. Okay, so let's erase that. Time and weights. So this means y1 is going to be e to the 2x, and then y2 is going to be equal to x e to the 2x. Now when we set up our variation of parameters, we know that this is going to be equal to y1 times u1 prime plus y2 times u2 prime is equal to 0. And then I'm going to have a y1 prime u1 prime plus y2 prime u2 prime is going to be equal to f of x. So I already know what y1 and y2 are. They're going to go, up in this top location. So this is going to be equal to, e to the 2x u1 prime plus x e to the 2x u2 prime is equal to 0. But I need to know these things' derivatives. So y1 prime, well, the derivative is 2e to the 2x. And then y2 prime is going to be the product rules. Derivative of the first times the second plus the first times the derivative of the second. So then we're going to have 2e to the 2x u1 prime plus, this coefficient, u2 prime. But this is going to be equal to f of x, which is right here. So I have x plus 1 e to the 2x. Now when we set these things up, we know that the determinant of w is going to be the determinant of this coefficient matrix. So it's going to be e to the 2x. This is x e to the 2x. We're going to have 2e to the 2x. And then this is going to be e to the 2x plus 2x e to the 2x. Now, which is going to equal a thing. Now, w1 is going to be, replace this first piece with, these. So this is going to be 0, x plus 1, e to the 2x. And then, the second's going to be unchanged. So this is going to be x e to the 2x. And this is e to the 2x plus 2x e to the 2x. And then our w2, I don't have room for it. That's fine. I'll put it right here. Our w2, and then its determinant is going to be equal to the determinant of, well, the first are going to be unchanged, but now the second column is going to be equal to this, so this is going to be 0, and then x plus 1 e to the 2x. So simplifying these, this, multiplying the main diagonal and subtracting the multiplication of the other diagonal. So what we're going to get is, do I want to do all the work? I can, but what we're going to get is kind of doing it down here, and I'm going to write this as e to the 4x, and just to save room, I'm going to show you that this is, e to the 2x times e to the 2x plus 2x e to the 2x. That's that main diagonal, and then we have to subtract, the minor diagonal, which is going to be x e to the 2x times, 2e to the 2x. So, e to the 4x, adding the powers, plus 2x e to the 4x, and then minus x e to the 2x, times 2, my bad. So minus 2e to the 4x. And we can see that those are going to cancel. That's why we get e to the 4x. Now, similar things can be done with this one. This w1 is going to be equal to negative x times x plus 1, negative x times x plus 1, e to the 4x, and then down here this one is going to be equal to x plus 1 e to the 4x. Which means that u1 was equal to, this w1 over the w, and this is going to be equal to, well, w1 is minus x times x plus 1 e to the 4x, all over, w, which is going to be e to the 4x, and we can see that e to the 4x's are going to cancel, so I have x times x plus 1 in the negative. So we can write this as, negative x squared minus x. And the reason why I'm going to write this is because this is actually w1 prime, and u1 prime, and I need to actually find u1. So u2 prime is going to be, w2 over, the determinant of w, w2 being right here, which is x plus 1 e to the 4x, and then w is going to be e to the 4x, so we can see that e to the 4x cancels, so this is just x plus 1. So finally, u1 is going to be equal to the integral of u1 prime, so it's the integral of x squared minus x dx, so this is going to give us negative x cubed over 3 minus x squared over 2, and then similarly, u2 is going to be equal to the integral of x plus 1 with respect to x. So this is going to be x squared over 2 plus x. which now allows us to find that y of p. So remember that y of p was going to be equal to, it's u1 y1 plus u2 y2. So now I know u1. u1 is going to be negative x cubed over 3 minus x squared over 2 times our solution function of y1, which is e to the 2x. And then similarly, plus u2, which is right here, this x squared over 2 plus x times our y2, which is going to be x e to the 2x. Finally, I can say my general solution, which is going to be equal to the complementary solution, which is right here, plus the particular solution, which is right here, is going to be equal to the complementary was, c1 e to the 2x plus c2x e to the 2x, plus now our particulars are going to be negative x cubed over 3 minus x squared over 2 times e to the 2x, that quantity, plus this quantity, which is going to be x squared over 2 plus x times this x e to the 2x. Now, to keep the video short, I'm not going to do another example, but I will do another example on this for a lecture very, very soon. And really our benefit, and kind of to show you what's going to come, is we have methods to be able to do this particular differential equation using, the family of functions of like some polynomial times an exponential. So we can, we have methods, but what this thing really helps us is what about doing something like this. Now, in a classic differential equations class, this is built of sines and cosines through division, not just through the addition. So this is superior in this way because I can use this method to solve this second order differential equation through a function that we tend not to do in previous sections. So if you like the content, please subscribe.